Okay, now the next topic is web caches or proxy servers. Now, in some networks, it's very useful to keep a server which plays the role of a cache. Now, what do we mean by cache? In microprocessor and in computer architecture, we know that cache is a small memory that is kept close to the microprocessor so that whenever a microprocessor require data to perform specific operations, it can find this data in the nearby small memory, which is the cache memory, and in that which is a hit. So in that case, it doesn't need to go to the main memory to bring the data. Accessing the main memory takes long time, more than the time it takes to access the cache. Now here, when we talk about proxy server, it plays the role of a cache, so that the objects that the client is interested in getting, we put them in a proxy server which is nearby, close to the client, so that if the client send the request for specific objects, and if it can find these objects in the proxy server, it's a hit. We don't need to send the request to the server, which could be far away from the client. So user sets browser web access via cache. Browser sends all HTTP requests to cache. So from now on, all the HTTP requests will be sent to the proxy server, hoping to find the objects that we are requesting in the cache server. So objects in cache, cache retains the object. Else, if the object is not in the cache, the proxy server is going to send the HTTP request to the server, which is going to respond with the object. Now we keep a copy of the object on the proxy server and we send it to the client. Later, let's say another client, which is this one, send request to the same object. It will find the copy of that object in the proxy server. So the proxy server will not forward this request to the origin server. It will respond directly with the object, which is going to save time. It is going to decrease the amount of traffic on the internet. Also, it's going to improve the performance, because the time it takes to send the object from the proxy server back to the client is much less than the time it takes to get the response from the origin server. Now, as an observation, we notice that the proxy server plays the role of both the client and server. When is it a server? If it has a copy of the object the client is requesting, it will respond. So it plays the role of a server. Also, it plays the role of a client. How? Let's say that the client is requesting an object that is not in the proxy server. In that case, the proxy server is going to play the role of a client, and it will send a request to the origin server, who's going to respond with the object, and the proxy server is going to store that object in its cache memory. Okay. Now, this is an example here which shows the advantage of using a proxy server. Let's say we don't have, in the first scenario here, we don't have a proxy server. And as you notice here, we have an access institutional network. Also, we have an access link, which exists between two routers. And also we have the public internet. Now, whenever a client from the institutional network sends a request to an origin server, how long would it take to receive the response? Let's assume that the average object size is 100 kilobits and the average request rate from browser to origin server is 15 objects per second. So here we are assuming that these clients at the institutional network are sending requests for objects. And where are these objects? They are located in servers in the public internet. How many requests the servers are going to get from these clients? 15 requests per second. So basically, we need to send 15 objects per second. And the average size for an object is 100 kilobits. Now, the average data rate to browsers is 1.5 megabits per second. Why? Because 15 objects per second, and the object size is 100 kilobits. So this 100 kilobits per object equals 1500 kilobits per second. So objects with objects. Now 1500 kilobits per second equals 1.5 megabits per second. Okay, now RTT from institutional router to any origin server, 2 seconds. Okay, now which means what? The public internet delay, so the delay here between this router and the origin servers is 2 seconds. So the RTT here equals 2 seconds. And the access link is 1.54 megabits per second, which is this. Okay. Also, it's clear that for the institutional network, the bandwidth is 1 gigabits per second. Okay. Now, the LAN utilization, what do we mean by LAN utilization? It's basically the amount of traffic we have relative to the capacity or the bandwidth. Okay. Now here we are talking about the LAN. So the utilization, how much traffic do we have that is caused by the 15 objects per second is basically the 1.5 megabits per second divide 1.5 megabits per second divided by 1 gigabits per second. So this is equal 1.5 by 10 to the power 6 bits per second divided by 1 by 10 to the power 9 bits per second equals 1.5 multiplied by 10 to the minus 3 equals 0.0015. So this is the utilization. How much traffic we have caused by the 15 objects per second relative to the overall bandwidth or capacity, which is the 1 gigabits per second. This is LAN utilization. Okay, now what about the access link, which is the 1.54 megabits per second? The traffic that is generated or caused by the 15 objects per second is 1.5 megabits per second. Megabits per second. Divided by the bandwidth of the access link, which is 1.54 megabits per second. Equals 0.97. Now, as you notice, there is a huge difference between the utilization in the LAN and in the access link. The utilization in the access link is 0.005, which means, if you remember when we discussed the traffic intensity, if you have very low utilization, which means the value of the traffic intensity is very low, we expect to have very small delays, almost negligible. For 0.0015, which is 15%, this is very small delays. And on the other hand, when we talk about utilization, which is 0.97, 97%, it's huge. And we are expecting the delays to be very high, which is basically minutes. And since the LAN utilization is 15%, then the expected delay is going to be what? In microseconds. Now the 2 seconds is coming from where? From the internet, which is given. So the overall delay is 2 seconds plus minutes plus microseconds, which means it's going to be minutes. And where is this minutes coming from? It's coming from the access link. Now, in order to improve the performance and decrease the delay, what can we do? We can increase the bandwidth on the bottleneck. What is the bottleneck in this example? It is the access link. Which means if we increase the bandwidth on the access link from 1.54 to something bigger, we are going to decrease the value here of minutes, hopefully make it smaller. So let's see the second scenario. We are here changing the capacity of the link, access link, from 1.54 megabits per second to 154 megabits per second. So 100 times bigger capacity. Now the same thing, the traffic that is generated by the 15 objects per second, where the object size is 100 kilobits, is 1.5 megabits per second. Now the same thing, whatever we have on the access network stays the same, which is going to be 15%. Very small utilization, which is going to cause the delay to be in microseconds. Now the 2 seconds for the public internet stays the same. What about the access link? Let's calculate the utilization. It's going to be the 1.5 megabits per second by 10 to the power 6 bits per second divided by 154 by 10 to the power 6 bits per second. So here we have equals 0.0097. So as you see here, the traffic utilization is much smaller, which means what? The delay that is going to be in the access link is not going to be minutes anymore. It's going to be much less, because when it was 97%, 0.97, it was minutes. Now it's 0.0097, much less than minutes, milliseconds. So now we have 2 seconds plus milliseconds plus microseconds, which is approximately, let's say, 2.01 second. Okay, which means if you increase the bandwidth of the access link, you are going to get an improvement in the overall delay, which is now 2.01 seconds instead of minutes in the previous scenario. Okay, but you know what, here there is a cost for increasing the bandwidth on the access link, so the cost will be higher. Okay, what about the case of using a proxy server? What if we use a proxy server? Now here in the third scenario, we are using a proxy server, as you see here. Now HTTP requests are going to be sent to the local proxy server, and if the object is found, there is no need to send these requests to the origin servers. Now let's assume that 40% of the requests are hit requests, which means what? We are going for 40% of the request, the object is going to be found on the proxy server. And for the 60% request, we need to send these requests to the origin servers. So 40% hit rate, 60% miss rate. Now in this case, we know that we have the 1.5 megabits per second, which is the traffic that is caused by the 15 objects per second. Now, how much traffic out of this 1.5 megabits per second is going to be sent to the origin servers? Actually 60%. 60% of the 1.5. So 60%, 0.6 multiplied by 1.5 equals 0.9 megabits per second. So only 0.9 megabits per second out of the 1.5 megabits per second is going to be sent through the internet. Because we have hit for 40%, the rest is going to be what? The 40% of the requests are going to be fulfilled within the local area network, within the LAN. Okay, now let's calculate the utilization. Let's calculate the utilization. Okay, for the LAN, we have the 0.9 megabits per second divided by 1.54. So here we are assuming that the bandwidth is 1.54 as in the first scenario. So 0.9 divided by 1.54 is 0.58. If you remember, without the proxy server, we had 0.97. Now it's much less, it's 0.58, which means the traffic intensity or the utilization is much smaller. So we don't expect it to be minutes anymore. It's going to be what? Milliseconds. What about? So this is what? For 40%. This is actually for 60% of the traffic. Okay, actually this is for 60% of the traffic. So for 60% of the traffic, we have 0.58, which is the utilization on the link, so it's not going to be minutes, it's going to be second. Now what about the 40%? Since the 40% is going to be fulfilled within the local network, so the delay is going to be in milliseconds, because the capacity of the local network is very high, 1 gigabits per second. So 40.4 multiplied by millisecond, and the 60% is going to be what? Sent to the origin server. Now, any request that is sent to the origin server is going to have 3 types of delays. The LAN here, which is going to be microseconds, and the delay which is on the access link. In this case, it's the utilization is 0.58, which means the delay is going to be in milliseconds. And we have what? The public internet delay, which is given, which is 2 seconds. Overall, for the 60%, we have the 2 seconds plus milliseconds plus microseconds. Total 2.01 seconds. So 60% multiplied by 2.01, and the 40% is multiplied by milliseconds. Actually, the 40% here is multiplying by approximately milliseconds or microseconds, to be consistent with the previous example, because in the previous we said what? In the access network, the delay is in microseconds. So here we can assume it's microseconds, which is negligible. So 0.6 multiplied by 2, approximately 1.2 seconds, which is basically coming from here. Okay. What's the conclusion? Having the proxy server, the overall delay is 1.2 seconds, which is less than that in the case of having increased the bandwidth at the access link 100 times, which was 2.01 seconds. So now it's what? 1.2 seconds, much less. Okay, which means adding a proxy server is going to give us an improvement that is better than increasing the capacity of the access link, which is the bottleneck here in this example. Okay, now the last thing that we are going to discuss in this section is the conditional get. There is a problem with proxy servers, which is when a client sends a request for an object, if the object exists in the proxy server, how can we be sure that this object is up to date? Maybe after the object was stored on the proxy server, it was updated in the origin server. Now in this case, we have inconsistent copy of the object on the proxy server. How can we solve this problem? Using conditional get. Now with conditional get, when the client send a request to the proxy server, so let's assume that this is the proxy, and let's say we have client here. So when the client send request to the proxy server, and let's say that the proxy server found a copy of the object, what the proxy server is going to do, he is going to send a conditional HTTP GET request to the server, asking the server if the copy he has, the proxy server has, is up to date. Now, if it was up to date, the server is not going to respond with the object. He's just going to inform the server that the object has not been modified, 304 not modified. So if the proxy receives this notification, this response from the server, 304 not modified, he's going to respond with the object to the client. Now, if the object has been modified, the server is going to send what? The object, and the response is going to be what? 200 OK. So the object will be sent back from the server to the proxy server, and the proxy server is going to respond to the client with the most recently updated object. Now the advantage here is that if the object is up to date, the server is not going to respond with the object. He's just going to respond with 304 not modified, which is not going to take as long as, which is not going to take time that is the same as the time it takes when the server sends the object. The time will be less, because sending a short response takes less time than sending the whole object back to the proxy server. Okay, this concludes section 2.2. Next time we start section 2.3.